So far we discussed the perceptron algorithm, and this algorithm worked in an online fashion. That means we are given a set of data points and serially we are giving the data points to the algorithm, and it adjusts the weight vector accordingly if the point is lying on one side of the hyperplane or the other, right. Now, what if we group all the set of data points together that are misclassified and we derive an update rule in a batch mode? That means instead of adjusting the weight every time in an online manner, we adjust the weight at one shot based upon the set of misclassified points. That leads us into another algorithm called the batch mode algorithm for the perceptron. So, let us start with the cost function for this. J is the cost associated and W is the weight vector. So, this is given by this quantity summation x belonging to the set of points that are misclassified. So, where H is the set of misclassified points. So, what I do is I take a negative of W transpose x and then I multiply this quantity by the desired value d that corresponds to this vector x, right. So, this d corresponds to this vector x. So, now what happens? So, if W transpose x is greater than 0, then it belongs to class C1 and our desired is 1, otherwise it is minus 1, right. So, in this case I negate it, and if it is misclassified, this is minus 1, but this value is positive, or it is plus 1 and this value is negative. So, therefore, I accumulate a positive cost because of the cost function j. Now, if all the points were correctly classified, of course, our misclassified set would be a null set, right. So, therefore, we would get 0 error, right. The cost would be essentially 0, otherwise we accumulate a positive cost. Now, what we do is the following: we take the gradient of this cost function. The gradient is with respect to the weight, and if we take the derivative, so this is going to be minus x times d corresponding to x over all x belonging to the set of misclassified points. Now, one of the important updates that I can do is motivated by the gradient descent idea, right. So, we have some cost function that we have, right. We do not know, not necessarily in this case a quadratic cost, right. I have to get at the optimal point, right. I can adjust the weight in such a way that I can get towards the optimal point, right. In this case the cost is really not quadratic cost, but again motivating through the example of the weighing balance, right. There should exist a solution where I can get to the right point that I can get after some iterations. So, what I can do is I can adjust my weight at time step n plus 1 to be my weight at time step n minus eta of n times the gradient of this quantity that I have with respect to the weight. So, this lends itself to this update rule, which is weight at time n plus 1 is weight at time n plus eta of n times the gradient. We will replace it with this function, which is sigma x times desired as a function of x for all x belonging to the misclassified set. Right. This is basically the idea behind the batch perceptron algorithm, and we will see shortly how this update rule gives us the correct update. So, the idea is pretty straightforward, and if we have digested the proof of convergence of the perceptron algorithm, it follows very similar to the proof of the perceptron algorithm, the convergence of the perceptron algorithm that we derived, and we will revisit it for the purposes of completeness. So, let us start with the proof of the batch perceptron algorithm. Now, we assume that the parameter eta remains the same for all n, and you have to sort of distinguish this time step n in the batch perceptron algorithm versus the time step n in the perceptron algorithm. In the perceptron algorithm, it was online, so every data point had a corresponding time step n. In the batch perceptron algorithm, we are grouping all the data points that are misclassified and then taking a cost and then evaluating the gradient of that function. So, therefore, it works in an epoch mode, and this n is the epoch that we think about, right. So, though we call it time step n, that is more an epoch because we are grouping all the misclassified points and then taking the derivative. Now, let us assume that this eta equals n, like what we did last time. Let the initial weight vector be W0, which is the all 0 vector. Now, let us consider this quantity W transpose x to be less than or equal to 0 and x belongs to the set of misclassified samples, right. We are assuming this belongs to class C1. So, when it is less than or equal to 0, then basically this is not correct, right. Now, W at time step n plus 1 is W at time step n plus sigma over all x, where x belongs to this misclassified set of points, right. This I should put an index which is going to be the set of misclassified points at time step n. Now let us expand this out like the way we did via recursion. So, this is going to be the summation of all those data points that are misclassified at time step 0 dot 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 summation of the misclassified set of points at time step n. So, the set H0 keeps varying, and that is an important distinction that we have to make when we think about the convergence proof of the batch perceptron algorithm, unlike the perceptron convergence proof where we just looked at the sample point by itself, right. Here it is the set which is changing, and the distinction has to be made very clear. Now, let us consider that there exists some W naught or W optimal or W 0, whatever you want to call. I will say W naught, the naught is in the subscript, right. Let us consider a W naught such that W naught transpose x is greater than 0 for all x belonging to class C1. Now, let us pre-multiply the equation that we had with W naught, W of n plus 1, right. So, let us pre-multiply this equation, I call this equation to be A. Let us pre-multiply equation A by W naught transpose. So, what we get is W naught transpose W of n plus 1 equals sigma W naught transpose x for all x belonging to this set H 0 plus dot 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 summation of W naught transpose x for x belonging to H n, right. Now, from here we follow the same steps, it is pretty straightforward. So, let us assume that we have we have a minimum of this summations, right. We look at all these individual sums, and there is a minimum for these individual sum, and let that be alpha. Let alpha be the minimum over all I summation of W naught transpose x for x belonging to some set H I in the process of this update. Okay. Now, by Cauchy-Schwarz inequality applicable to the left hand side of equation B, so what we get is norm W naught square times norm W of n plus 1 square. This is going to be greater than or equal to n plus 1 square times alpha square. Now, you can rearrange these terms. So, this is at least n plus 1 square alpha square upon norm w square, right. Let me call this equation C. So, we follow straightforwardly like what we did in the other proof, but the care that we will have to take is how the sets change as a function of your epoch. Now, we start with this recursion Wn plus 1 is Wn plus summation over all x, x belonging to Hn, right. We take the norm on both the sides, norm square. So, norm of Wn plus 1 square is going to be norm Wn square plus summation sigma over x belonging to Hn, this norm square, plus 2 times W transpose of n summation over x, x belonging to Hn, right. But we know that this quantity is less than or equal to 0, right, because we assumed that to start with. So, therefore, norm of Wn plus 1 square is less than or equal to norm Wn square plus norm sigma over x, x belonging to the set of misclassified points at time step n square. Now, we do this recursively like what we did earlier. So, we will land up with norm Wn plus 1 square is less than or equal to the summation from I equals 0 to n, the norm of x, x belonging to Hi, this squared. Now, let us choose a quantity beta to be maximum over all I, the norm of summation over x, x belonging to this set of misclassified points at time step I, right. With this adjustment, we land up with the Euclidean norm at time step n plus 1 square is at most n plus 1 times beta. So, let me call this equation D. Now, we have D and we have an earlier equation inequality which is C. Now, from C and D, there should exist an n, I would say n max, that is maximum number of epochs, such that the inequalities satisfy the equality condition. So, working this out, it is exactly the same. N max happens to be beta upon alpha square norm of W naught. W naught is your optimum vector square minus 1, and you can put a seal on this quantity so that it is an integer and things are all satisfied, right. So, this proves that the batch perceptron algorithm converges after n max iterations. And one thing that you should note very carefully, I think from implementation perspective, I think I would just mark them as notes. In the batch perceptron algorithm, n is on an epoch basis, that is, you group all the misclassified points and then do an update based on a gradient. Of the cost. Whereas in the ordinary perceptron algorithm, n is the online time step where data is presented to the neural network. Okay, this is a very important distinction, and while you code it, you will realize that you will have to make these time steps carefully done. Okay, so we have covered the perceptron and the batch perceptron algorithm. So, which algorithm you will adopt is dependent on which application you are interested in, whether you want to do it online or you want to do it on a batch mode basis. But recall, if you are doing a batch mode basis, you can also parallelize the algorithm, and there are some natural advantages. We will discuss the general idea behind batch and online algorithms when we discuss with the multi-layer perceptron, or when we discuss the backpropagation algorithm. We will talk about the nuances between online learning and batch learning.